Chapter 6, Module 3. This module is a preamble to the construction of fundamental group of a circle. For constructing fundamental group of a circle, we need to scrutinize a function, a very well-known function called exponential map from the real line R to the unit circle S1. In this module, we shall discuss several properties of this exponential map and thereby get the definition of what we call degree of a loop. In what follows, by S1, we mean the unit circle described as all the points Z in the complex plane having the modulus value 1, or by the ordered pair cos 2 pi t sin 2 pi t, where t varies over the closed interval 0, 1. Also, by P0, we mean the complex number 1, that is the ordered pair 1, 0, and we define the exponential map as usual, that it takes any real number t to cos 2 pi t plus I sin 2 pi t. We begin our discussion by enlisting a few facts about the exponential function. First of all, exponential is a continuous surjection. Secondly, exponential of s plus t is equal to exponential s into exponential t. Exponential of any integer n is P0. Exponential wraps the real line R anti-clockwise around S1 as depicted in this figure. If U is a proper open subset of S1, then exponential inverse U is a disjoint union of open intervals of R, and U is homeomorphic to each of these open intervals. In particular, if U is S1 minus 1 and V is S1 minus minus 1, then exponential inverse U is the disjoint union of all the open intervals n to n plus 1, where n is equal to minus infinity to plus infinity, and exponential inverse of V is the disjoint union of the open intervals n minus half to n plus half, where n varies from minus infinity to plus infinity. In particular, exponential maps minus half to half, this open interval, homeomorphically onto S1 minus minus 1. Since it is a homeomorphism, its inverse exists in this interval, and so we denote the inverse by LG, which goes from S1 minus minus 1 to the open interval minus half to plus half. And of course, if we put 1 in this inverse, then that will give me back the value 0. Later on, we shall see that exponential map is a particular example of what we call a covering projection. So, real line becomes a covering space of the unit circle S1. We shall also see in some subsequent module that covering projection has a very interesting property, what we call path lifting property. So, an exponential map possesses path lifting property. The proof of this path lifting property is quite difficult, or rather it involves lot of concepts. Here we shall give one elegant and very simple proof of path lifting property, specially for exponential maps. We now state path lifting property for exponential map. For any continuous function g from the closed interval 0, 1 to the unit circle S1 with the value g0 equal to exponential of x for some real number x, there exists a continuous function g cap from the closed interval 0, 1 to r such that g cap evaluated at the point 0 is the same point x, and exponential composed g cap is equal to g. That is, the diagram shown here commutes. This g cap is called a lift of g. Let us prove this result. Since I is compact and g is a continuous function, we know that g will be uniformly continuous. So, for any epsilon, in this case we choose epsilon as 2, there exists delta such that whenever mod s minus t is less than delta, we have norm gs minus gt less than 2. As gs is on S1, norm of gs will be equal to 1, and consequently gs and minus gt cannot be equal whenever s and t satisfy the condition mod s minus t less than delta. Choose any n such that n delta is greater than 1, and that is possible by Archimedean property of real line. Then for all t and for all j from 0 to n minus 1, we have norm g plus 1 by n t minus g by n t is less than delta, so that g of j plus 1 by n t cannot be equal to minus g of j by n t. Hence, j plus 1 by n t divided by j by n t cannot be equal to minus 1. Also, norm of this point is equal to 1, which implies that this point j plus 1 by n t divided by j by n t is a point on S1 minus minus 1. Consequently, the inverse of exponential in that particular region operated on that point will give me a point in the open interval minus half to plus half. Now we define g cap from I to r by this formula, that g cap t is equal to x plus summation of the inverse of the exponential evaluated at that point g of g plus 1 by n t by g of j by n t. Then g cap of 0 is equal to x, and for all t belonging to I, exponential composed g cap evaluated at t will be equal to gt. Therefore, exponential composed g cap is equal to g. That is, g cap is the desired lift. Now we check the uniqueness of g cap. If possible, suppose there is another lift g tilde of g. Then of course, by the definition of lift, exponential composed g tilde is equal to g, and g tilde at the point 0 is equal to x. So, for all t belonging to capital I, these two functions, exponential composed g tilde and exponential composed g cap, will have the same value. That is, exponential of g tilde t minus g cap t will be equal to 0, so that by the property of exponential map as discussed earlier, g tilde t minus g cap t will be an integer. In other words, g tilde minus g cap, this function, since both are continuous function, this difference is again a continuous function, will take the closed interval I totally inside the set of integers z. Now, we know that continuous function takes a connected set to connected. Now, I is connected, g tilde minus g cap is a continuous function. So, g tilde minus g cap of I will be a connected subset of z. But z is totally disconnected, and therefore, g tilde minus g cap of I is a singleton subset of z. Moreover, g tilde minus g cap evaluated at the point 0 is g tilde 0 minus g cap 0, that means x minus x, and therefore it is equal to 0. Hence, g tilde minus g cap t is equal to 0 for all t in I, thereby giving that these two functions are same. One may observe that in the proof of path lifting property, if I is replaced by a compact convex subset of Rn, then the result holds and the proof remains exactly the same. So, taking I cross I instead of I, we can construct the lift for a continuous function capital H, which is a map from I cross I to S1, thereby obtaining a theorem what we call homotopy lifting property of the exponential map. It says that for any continuous function capital H from I cross I to S1 with H00 equal to 1, there exists a unique continuous function H cap from I cross I to R such that H cap 00 is 0 and exponential composed H cap is equal to H. Now we can see that how efficiently we could use this path lifting property of exponential map to define degree of a map f from S1 to S1. We shall also see that this definition of degree of a map will lead to the definition of what we call degree of a loop. Now, a unit circle S1 can be viewed as a quotient space of the closed interval 0, 1. How do I get the identification? If we take the closed interval 0, 1 and glue the points 0 and 1 together, then we will get a circle. So, there exists a continuous surjection called the quotient map, which we denote by pi, such that pi 0 is equal to pi 1. Now, let us take f as a function from S1 to S1, which is continuous. Then, if we compose f with the quotient map pi, then f composed pi will be a function from I to S1. This composition f composed pi we denote it by g. This is again a continuous function with g0 equal to g1. Now we are applying path lifting property of the exponential map to get a unique lift g cap from I to r such that exponential composed g cap evaluated at the point 0 is equal to exponential composed g cap evaluated at 1, because exponential composed g cap is equal to g by the definition of a lift. Now taking exponential of g cap 1 minus g cap 0, we have that it is having the value 1. Again, by the property of exponential map, whenever it takes anything to 1, that should be an integer. So, g cap 1 minus g cap 0 is an integer. Now, we show that this integer g cap 1 minus g cap 0 depends only on f, not on the lift. For that, suppose g0 is x, which is on S1, and we take y, z 2 points from R such that exponential evaluated at y is equal to exponential evaluated at z, and these two are having the value x. Then there are lifts g cap and g tilde of g such that g cap 0 is y and g tilde 0 is z. Also, exponential composed g cap, this is equal to g, and exponential composed g tilde is the same g. Therefore, g cap 0 minus g tilde 0 is an integer. So, g cap 0 is equal to g tilde 0 plus that integer n. Now, this gives that g tilde plus n is another lift of g such that g tilde plus n evaluated at 0 is g cap of 0, and that is equal to y. By uniqueness of the lift, we then have g cap is equal to g tilde plus n. Hence, g cap 1 minus g cap 0 is g cap 1 plus n minus g tilde 0 plus n, which gives g tilde 1 minus g tilde 0. Since this value, this integer is independent of the choice of the lift, we now define degree of the function f by that number. That is, for any continuous function f from S1 to S1, we define degree of f or winding number of f by the unique integer g cap 1 minus g cap 0, where g cap is the unique lift of f composed pi. Here, this pi stands for the quotient map. In particular, if alpha is a loop based at the point 1, there exists a unique lift alpha cap from I to r such that alpha cap 0 is equal to 0 and exponential composed alpha cap is equal to alpha. So, we have the definition for degree of loop as this one, that for any alpha a loop in S1 based at 1, the unique integer alpha cap 1 is called the degree of alpha, denoted by degree alpha, where alpha cap is the lift of alpha such that alpha cap 0 is equal to 0. So, in a nutshell, we have discussed several properties of exponential map, giving special emphasis on two very important properties. One is path lifting property and the other one is homotopy lifting property of the exponential map. In the subsequent modules, we shall see the usefulness of these two properties. We have also defined what we call degree of a loop. As pointed out in the beginning of this module, that for construction of fundamental group of S1, we need these concepts.